After getting the equation for a closed system work, which is work done is equal to integration of PdV, and a closed system work, that is integration PdV, is only applicable for a reversible process, and we already see that the work done will be equal to the area under the PV diagram when the area is projected on the volume axis. Now we are going to study what are the work done by the system for various processes. There are so many processes in the thermodynamics, just like constant volume process, constant pressure process, isothermal process, adiabatic process. So there are lot of processes which we have to study in your thermodynamics. So we will go one by one. First of all, we will see the work done in constant volume process. As the name suggests, that constant volume, it means your volume is constant. Volume of the system is constant, volume is not changing. Any other thing, any other property will be changed or will not be changed, but the volume is constant. So as we know that work done is equal to integration PdV, that is applicable for closed system and reversible process. We know that this is applicable for closed system and reversible process. If the volume is constant, this is dV, that is change of volume. If volume is constant, then the change of volume will be 0. If the change in volume will be 0, so we can say that work done by the system or work done on the system in a closed system process of a constant volume process will be equal to 0. Work done by the system in a closed system constant volume process is equal to 0 because there is no change in volume. So this is the first example, first process, that is constant volume. Now the second process will be constant pressure, or you can say that isobaric process. As the name suggests, it is a constant pressure, that means pressure will be constant. Throughout the process, when the process is going on, throughout the process, at each and every point, the pressure will remain constant. Volume will change, temperature will change as per the equations, but pressure will remain constant. So this is also known as an isobaric process. So as we know that work done is equal to integration PdV, which is applicable for closed system reversible process. If I am saying that if our pressure is constant, so we take out this pressure outside the integration because it is a constant value. So we will take this pressure outside the integration. So the work done will be equal to pressure integration of dV, and integration of dV is equal to volume V. And if I put the limits for a process that is from point 1 to point 2, if a process is going from a point 1 to point 2, so if I put the limit, so integration of dV is V, and if we are putting the limits, that is equal to V2 minus V1, upper limit minus lower limit. So work done in a constant pressure process will be equal to pressure into change of volume, that is V2 minus V1. So work done is equal to P into V2 minus V1, that is applicable for closed system and reversible process. These assumptions are very important, that this formula will only holds good when the system is closed and when the process is reversible. If the system is open, there is some mass transfer, this formula will not hold good. So this is the constant pressure work transfer. And one more thing, this is a work done by the system. So this is P into V2 minus V1, closed system reversible process. Now the next our third process is a isothermal process. Isothermal process is that process in which your temperature is constant. We have that constant temperature process known as isothermal process. Now in isothermal, your temperature will remain constant. Temperature will remain constant throughout the process. So let us say we are taking the example of an ideal gas. We'll see ideal gas later on, but as far as basics are concerned, we know that ideal gas equation is PV is equal to mRT. P is pressure, volume, M is your mass, R is your characteristic constant, and T is your temperature. So in a isothermal process, if this temperature is constant, mass is constant, R is a constant, if temperature is constant, so we can say that PV is equal to some constant C, right? Because this right hand side will be a constant, so I am writing PV is equal to some constant C. So for a isothermal process, if a process is going from point 1 to point 2, initial point is 1, final point is 2. So we can say that for a isothermal process, if PV is equal to constant, for a process from point 1 to point 2, I can write P1V1 minus P1V1 will be equal to P2V2, and which is equal to MRT, because it is a constant value. So P1V1 is equal to constant, P2V2 is equal to constant, and which is this constant will be equal to MRT. So we can rearrange this, that P1 upon P2 is equal to V2 upon V1. So I just rearrange this one. Now we want to know what is the work done in a constant temperature process, or a work done by the system in a isothermal process. So we know that work done is equal to integration of PdV. When we are using this constant, when we are using this as a closed system and reversible process. So in place of P, I am writing this PV is equal to constant. So from here I can write P is equal to C upon V. So P is equal to C upon V. From this equation I can write P is equal to C upon V into dV integration from point 1 to point 2. This is the work done in a constant temperature process. I am just substituting this P is equal to C upon V. Now C is a constant, we can take C out. So this is will be equal to C into integration of dV upon V from point 1 to 2. This is integration of dV upon V from point 1 to 2, and we know that the integration of 1 by x or 1 by V is equal to ln V log V. So if this is equal to ln V and I am putting the equation, I am putting the limits from 1 to 2, so I can say that work done will be equal to C into ln V2 by V1. Right? If we are solving this, we will get work done will be equal to C, that is some constant. Here this is C. C is P into V, which is equal to MRT, or which is equal to P1V1 is equal to P2V2 is equal to MRT is equal to some constant. So this C is into ln V2 upon V1 will be the work done. So C will be P1V1, it may be P2V2, it may be MRT. These are the only, I am just substituting the value of C. These all of the three are equal. So I am just substituting the value P1V1 or P2V2 or MRT ln V2 by V1. So work done in a constant temperature process will be equal to MRT ln V2 by V1, or you can say that from here V2 by V1 will be equal to P1 by P2, right? So I can substitute this will be equal to MRT ln, in place of V2 V1 I am writing P1 by P2, right? From this equation V2 by V1 is equal to P1 by P2. So V2 by V1 I am substituting as a P1 by P2. So this is the constant temperature work done in a closed system. The most important thing is the assumptions of using this equation. The assumptions of using this equation, that constant temperature or isothermal work done by a system will be equal to MRT ln V2 by V1. The assumptions are, in this case we are assuming first equation, that is ideal gas equation, right? These formulas are coming when we are considering that our gas is an ideal gas. If our gas is not an ideal gas, so this formula will not hold good, so this equation will not hold good. This equation will carry forward after assuming that the gas is an ideal gas. So first assumption of this formula is your ideal gas, because I am taking here. So first assumption, most important thing is ideal gas. These works, that is your constant volume work, constant pressure work, in these works I am not taking ideal gas assumptions. I am just deriving for any substance. In this case that system will be of any substance, air, hydrogen, nitrogen, anything it would be. But in constant temperature, if you are using this formula for your work done, then the gas must be an ideal gas, right? First equation is your ideal gas, first assumption is your ideal gas. Second assumption is we are using this formula for work done. We using this formula for work done for this derivation. So this formula is only applicable for closed system and reversible process. So This formula, there are three assumptions to use this formula. First one is system must be closed, system or the process must be reversible process, and that material must be an ideal gas. If the material is an other gas rather than your ideal gas, this formula will not hold good, right? So this is a constant temperature work done. Next, fourth process is your adiabatic process. There is one process in your thermodynamics which is known as an adiabatic process. Adiabatic process is that process in which there is no heat transfer. Heat transfer will be zero, means no heat is going out of the system and no heat is coming in the system. Both ways your heat transfer is zero. Work may be transfer, may not be transfer. Work transfer can take place. Only heat transfer will not take place. Those processes are known as your adiabatic process. So in adiabatic process there is no heat transfer, and for adiabatic process the equation will be PV raised to power gamma is equal to constant. We'll derive this equation later on, right? When we are studying that what is the heat transfer, heat interaction, when we are studying, we derive this equation there. For as of now, for reference, for adiabatic process, equation will be PV raised to power gamma is equal to constant. P is your pressure, V is your volume, gamma is your adiabatic constant, some constant is there, and this gamma must always be greater than 1. This is always greater than 1, and for air this gamma will be equal to 1.4. For air this gamma will be equal to 1.4. You have to remember this value. For air gamma is equal to 1.4. So this PV raised to power gamma is equal to constant. We'll see later that when we are deriving this equation, that is PV raised to power gamma is equal to constant, we are taking two assumptions. First assumption is your reversible process. Process must be reversible, and second assumption is gas must be an ideal gas. If the gas is not an ideal gas, this formula that PV raised to power gamma is equal to constant will not hold good. So this equation, this formula is only used for reversible process and ideal gas. You have to remember all the assumptions, because when you are solving the numericals, these assumptions will be most important. If the assumptions are deviating and you are using this formula, and in the question it is given that it is not an ideal gas, other gas is given, and still you are using this formula, that numerical will go wrong, right? So this PV raised to power gamma is equal to constant will holds good only for an ideal gas and a reversible process. Now this gamma is equal to Cp upon Cv, we'll see it on later on. Cp is your specific heat at constant pressure, and Cv is equal to specific heat at constant volume. We'll see it on later on, what is the meaning of specific heats and what is the meaning of Cp and Cv. Just for a reference point of view, I'm just writing here. Now we want to know what is the work transfer work done by the system on the surrounding in an adiabatic process. So we know that in a closed system, work done is equal to integration of PdV from point 1 and 2. Assumptions of using this is your closed system and reversible process. Assumptions of using this formula is closed system and reversible process. Assumptions of using this formula is reversible process and ideal gas. Now we have that PV raised to power gamma is equal to constant for an adiabatic process. So I can write pressure is equal to C upon V raised to power gamma. I take this V in the denominator. So P is equal to C divided by V raised to power gamma. I put this value of P here, then work will be equal to integration from point 1 to 2, initial state to final state, C V raised to power minus gamma. If this V goes in the numerator, that power will be negative. V raised to power minus gamma into dV. C is a constant, we can take it out from the integration part. Integration of V raised to power minus gamma into dV is, we know that this is equal to V into this power minus gamma plus 1 divided by minus gamma plus 1. This integration, basic integration of x raised to power n. Basic integration of x raised to power n, we know that this is equal to x raised to power n plus 1 divided by n plus 1. This is the basic, we all know that integration part, right? So the integration of V raised to power minus gamma is V raised to power minus gamma plus 1 divided by minus gamma plus 1 from point 1 to 2. Now if I am putting this from point 1 and 2, so this will be equal to C into upper limit first V2 raised to power minus gamma plus 1 minus lower limit V1 raised to power minus gamma plus 1 divided by 1 minus gamma or minus gamma plus 1. So this is the thing. Now I take C inside. Now I divide this equation with C. Now I am taking C inside. I am multiplying these two with C. Suppose this is the case. I am taking C inside. And what is C? C is PV raised to power gamma is equal to constant. From here I can write P1 V1 raised to power gamma is equal to P2 V2 raised to power gamma is equal to constant. PV raised to power gamma for a process is constant. For a process, when the process is undergoing from point 1 to 2, PV raised to power gamma is equal to constant for an adiabatic case. So at each and every point, PV raised to power gamma must be constant. So I am writing P1 V1 raised to power gamma is equal to P2 V2 raised to power gamma is equal to constant. So this C, here I write C is equal to P2 V2 raised to power gamma. This is C. I am just solving this. This is C. And here this C I am writing P1 V1 raised to power gamma. Right? Only I am just putting the value of C here. So from here if I solve it further, V2 raised to power gamma into V2 raised to power 1 minus gamma will be equal to, power will add, this will be equal to P2 V2 and this will equal to P1 V1. So this is, if I rearrange, if I take minus sign out, so this is work done in an adiabatic process. Adiabatic process means your heat transfer will be 0. So work done in an heat transfer will be 0 in an adiabatic process will be equal to P1 V1 minus P2 V2 divided by gamma minus 1. Right, this is the formula for your work transfer. The assumptions of using this work transfer is, right, we are taking this derivation. The assumptions are, we used first formula we are using this PV raised to power gamma constant. For this two assumptions, reversible process, ideal gas. So as using this formula must be, the assumptions must be reversible and ideal gas. And now next we used this formula. For this two assumptions are there, closed system and reversible. Reversible we already taken, so the system must be a closed system. So using this formula as a work transfer in a adiabatic process, three assumptions we are taking: ideal gas, reversible process and closed system. So only in that case this formula will holds good. If process is irreversible or the gas is not an ideal gas or the system is not closed, this formula will not holds good. Last process for the thermodynamics point of view is your polytropic process. We already see the work done in constant volume process, constant pressure process, constant temperature or isothermal process, and fourth one is your adiabatic process. This is the last process, which is polytropic process. Polytropic process are those processes in which your pressure and volume follows the relationship of PV raised to power n is equal to constant. In adiabatic, the same relation is there, but there is gamma. That relation is PV raised to power gamma is equal to constant. But in case of your polytropic process, the relationship is PV raised to power n is equal to constant, where n is your any polytropic index. N is polytropic index. There in adiabatic process, gamma is your adiabatic constant or adiabatic index, and here n is your polytropic index. The basic difference between a polytropic process and an adiabatic process is, in adiabatic process there is no heat transfer, only work transfer will be there. But in case of your polytropic process, both heat and work transfer can occur simultaneously. So in polytropic process, heat transfer will be there, but in adiabatic process there is no heat transfer, only work transfer can take place. So this is the basic difference between a polytropic and your adiabatic process. And we see later on all the process like your constant pressure, constant volume, isothermal process, adiabatic process, all those processes can be defined in terms of a polytropic process. So PV raised to power n is equal to constant is a polytropic process, and generally this value of this n will be greater than 1 and less than your gamma, that is your adiabatic constant. But usually n can vary from minus infinity to plus infinity. It will depend upon the process to process, but generally n will be between 1 and gamma. It will be greater than 1 and will be less than gamma, right? So we have to derive the equation for the work transfer done by the process, done by the system in a process if the process is a polytropic. So we can derive like the same as we did in your adiabatic process. Then I am just writing the direct result. The only difference is there is gamma, here is n. So the formula will be coming that W is equal to P1 V1 minus P2 V2 divided by n minus 1. There work done in adiabatic process is, if heat transfer is 0, their work will be P1 V1 minus P2 V2 divided by gamma minus 1. So in place of gamma in polytropic process, that is n. So the work will be P1 V1 minus P2 V2 divided by n minus 1, and the assumptions will remain same as that of your adiabatic process, that is closed system, process must be reversible, and the material would be ideal gas. This equation PV raised to power n is equal to constant holds good for an ideal gas and a reversible process. So this formula will be valid only for a closed system, ideal gas and a reversible process. If any of the assumptions will not hold good, this formula will not be valid in that case. So this is the work done by a polytropic process by a system on a polytropic process. So these 5 we can discuss in your thermodynamics: the work transfer or work done by the system or on the system if the system is closed. So we discussed 5 different types of process. Now if I just brief this discussion, right, we see that work done is equal to integration of PdV. This is a generalized formula, that is integration of PdV. Assumptions of using this one is closed system, reversible process. Now the work done in a closed volume process is, the work done in a closed volume constant process is 0. We see it earlier. Assumptions are closed system, reversible process. Work done in a constant pressure process is P into V2 minus V1. Assumptions are same, closed system and reversible process. Work done in a constant temperature process or an isothermal process is P1 V1 ln V2 by V1 or P2 V2 ln V2 by V1 or MRT ln V2 by V1. So these are the one and the same thing. The assumptions of using this formula is closed system, reversible process. One more assumption adds here, which is ideal gas. If the gas is not ideal, you cannot use this formula for your isothermal case. In that case, we have to go with the derivation, right? We'll see later on with the help of some numericals that when temperature is constant but the gas is not an ideal gas, how to find the work done by that closed system, by that system on a process in which temperature is constant but gas is not an ideal gas. So in that case, we are not using this formula. This is only valid for an ideal gas. If it is mentioned in the question that the gas is not an ideal gas or some other thing it is mentioned, so you cannot use this. We will do with the help of this formula, because this general formula of integration PdV doesn't require the gas should be ideal gas. It is valid for all the materials, be it air, be it ideal gas, hydrogen, nitrogen, be it anything. So this formula holds good for all the material, but this formula holds good only for an ideal gas, right? So work done in a heat transfer constant, work done in an adiabatic process in which there is no heat transfer will be equal to P1 V1 minus P2 V2 divided by gamma minus 1. There are 3 assumptions of using this: closed system, reversible process and ideal gas. These 3 assumptions will holds good. Then we can use this formula for an adiabatic process in a closed system. This is the work done in a closed system for an polytropic process. Polytropic process means both heat and work transfer can take place. So this is the formula is P1 V1 minus P2 V2 divided by n minus 1. Same three assumptions are there: closed system, reversible process and ideal gas. So these assumptions you should take care while solving the numericals. If the assumptions are deviating, so you cannot use the direct formula which we are writing for the all 5 process. If the assumptions are different, if the gas is some other gas, so we will start with our basics, that is work done is equal to integration PdV, and from there we can go proceed further, right? This is all about your thermodynamic work and work transfer in different types of process.